Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step on inside as we go to our sections 10.1 to 10.3 quiz review in the Big Ideas Math Integrated Math 2 textbook. These are things regarding circles, specifically, I don't remember what the name of the section was in 10.1, but like segments and lines that intersect in circles was kind of the idea of it. And then we did finding arc measures in section 10.2, and 10.3 was using chords. So with all of that in mind, let's take a look at the, I think, 19 problems that they have in this section here. If you want to find this actual page and you don't have it on hand with yourself, go ahead and download it in the description section below. It should be right up top there, and you can, of course, write these things down as you need to. And if you want to find a specific problem with this, I have them either in the time slider or in the timestamps in the description section down below as well. Go to the actual lecture portions in my playlist for IM2 if you want to learn more about this material. I might go pretty quickly with it as an overall. These kind of go pretty quickly, all depending on the problems. Without further ado, I'm going to go ahead and get started. And we're going to take a look at numbers 1 through 6. They tell you what section it's out of. They say use the diagram and we'll name the circle. So on number 1, name the circle. The circle is named by its center. Now, it is a circle, so they call it circle whatever. You can either use the word or this symbol. They literally draw a circle. They put a little center in like that. And the center here is P, so this is actually called circle P. That is actually its name. And that's it. These first 6 are going to go very fast, actually. I'm very excited about that. Number 2, name a radius. Keep in mind, there's an infinite, literally, no pun intended. No pun intended. Literally, not hyperbole. There is an infinite number of radii in the circle, but as far as ones that are drawn, ones that we can see and use and do, from P to K would be a radius. Here's one of them, segment PK. You see a radius goes from the segment to any point on the circle. K is on the circle right here. It's a point, and from P to K would be a radius. Also, we can do from P to N. Sorry, that's not very well drawn. But from P to N, that would be another radius. Okay. You could make up other radii here. It says do a radius. It doesn't have to be a segment that's drawn. You could make one from P to J, from P to L, from P to another made up point. So kind of in a superfluous way, from P to J and from P to L can also be done. All those kinds of things can work for number 2. Those are all radii. Number 3, name a diameter. I'll go as particular as the one that they have here. P to K and P, K, and N, they are all collinear points. They are a segment drawn through the center. That is the diameter. So you name a diameter from one endpoint to the other. So I can say KN or NK. That's really the only one I'm looking to do. I can't guarantee any other points that go through the center. Number 4, name a chord. Now, chords are segments drawn, any segments that are drawn in your circle from one point on the circle to another. The diameter being the longest chord, so I could use KN again as an answer. But a unique chord that's not a diameter that you can see here is from J to L. From J to L, and I'm not going to name other ones, but from J to L, segment JL is a chord. It goes from one part of the circle to the other, one point on the circle to the other. KN would be one. However, I'll keep it with diameter. Number 5, name a secant. A secant is a line that intersects your circle at 2 points. It goes in, out, and through. So for instance, this one right here, from S through K and P and N and through Q and onward like that, this is a secant line. It goes through twice, or it touches the circle twice. So I'll go with points we haven't named before. I'll call this line SQ. That one works out for me. I could name this any of those 2 points that are on this thing, and it would qualify. I could have called it SK, SP, SN, SQ, KP, KN, KQ, PN, PQ, or NQ. As long as I had a line on it, they would have all been good. And number 6, name a tangent. A tangent is a line or ray or segment that would intersect the circle at just one point. The way that I say it is it kind of just kisses and goes, right? At point M, it just touches the circle at that one point, and that's it, and it just goes through. So this, you could imagine, is a tangent right here. So I could use something like the points M and R and call it line MR, like Mr. something like that. That works out, or MQ or QR. I like to use the point that's actually the tangent on there, so I probably wouldn't say QR. It's fine. It's just emphasizing that M is the point of tangent C would be nice. All right, that could have gone a lot faster, but I wanted to kind of review with that. Let's go to number 7. They say find the value of x. And number 8, of course, find the value of x. But they're two different kinds of problems. They both involve tangents. On number 7, well, they draw some things for you, which is very helpful. But what they draw is a right triangle. But it's really about a tangent line intersecting a radius at a 90-degree angle. Now, they show you these x's as well. They represent the radii of your circle. Now, as a right triangle, Pythagorean theorem can come into play. A squared plus b squared equals c squared. But this hypotenuse is x plus 9. And so we're going to square all of x plus 9. So 15 squared is 225, excuse me. And x plus 9 quantity squared expands to x squared plus 18x plus 81, something you'd have to remember from your perfect trinomial expansion of your. The x squareds can cancel as terms because they both subtract from both sides. And I don't always love to use the word cancel, but it's fine here if you understand what's happening. And I'll subtract 81 from both sides, and I get 144. Yeah, I think that's right. I was about to take the square root of both sides, but we're dividing by 18. Dividing by 18, and I don't know what that number is. I don't know. Let me use a calculator. I could reduce the fraction. I probably should reduce the fraction. Let me see. Okay, it's 8. That's what I wanted to check first. Is it an integer? It is. I don't know why I overthought that. Okay. I'm generally really good at that. I just wasn't confident that it was an integer. Number 8. This is a different kind of question. Yes, there are radii intersecting with tangents. However, this time it's about the lengths of these tangents being equal to each other. Any two tangents that intersect at some external point like this have congruent segment. They're equal lengths. You set 6x minus 3 equal to 3x plus 18, and you solve for x from there. Subtract 3x from both sides, you get 3x equals 21, and divide by 3, you get x equals 7. Sorry I'm stumbling over my words today. I'm just kind of antsy to get her done. That was section 10.1 as well. Now let's move on to section 10.2 for numbers 9 through 14. They say identify the given arc as a major arc, minor arc, or semicircle, then find the measure of the arc. So on number 9, we have arc AE. Let's look at it in the diagram. I'm actually going to bring the diagram out onto my other portion of this, probably mark it up a little more so. So right there, the measure of arc AE. Well, let's not talk about the measure first. Let's talk about the arc itself. We're talking about this guy right here. Now, you might wonder, it's from 80. You might wonder how we know we're not talking about this one. Well, I'm going to answer that first question, what they ask for, major, minor, or semicircle. It's a minor arc, and I know that because this is 2 letters. 2 letters is automatically grounds for a minor arc, period, unless you guys write it and you do it incorrectly. But if a book or whatever's going to write it, they're going to do it that way. So I know the minor arc is from A to E in the minor area, the one that's less than a semicircle, one less than 180 degrees. Now, what is its measure? That's what we wonder next. Measure of arc, I do this a lot, AE. I turn a C into an E. Here's what I kind of noticed. I mean, you have 2 options. You can, well, we don't know this measure actually, so I'm not going to speak on that one. So let's go to the one option that I kind of want to play with right now. We know this is a diameter. Therefore, this whole thing's a semicircle. And maybe they'll ask about it later. I have no idea. But this whole thing's a semicircle, whose measure is 180 degrees. So we take the 180 and we subtract the 36 that's right here, because 180 minus 36 will be this result there. And that actually is 144 degrees. We just saw that number a second ago for a way different reason. But measure of arc AE is 144 degrees. Number 10, arc BC, also a minor arc because it is 2 letters long. The semicircles in major arcs are 3 letters long, but arc BC is also a minor arc. This is that one that we didn't know anything about. I think what would be very helpful for us in this situation, well, actually, no, it wouldn't necessarily, but I'm going to put the 144 here because now that we know that value. Let's use the other semicircle this time. In arc BC, this is what we're trying to find, but note that we have an entire semicircle here, and 67 and 70 can be subtracted from that semicircle, and we can then go ahead and find this thing. So let's do 180 minus the sum of 67 and 70, which is 180 minus 137, which is 43 degrees. And that's the measure of arc BC. Let's go to number 11. I probably need to bring my diagram down here. Let's just do another one. I got a bunch of them. Now we know these measures. We got a 43, and these stick in the rest of the problem, right? So 43 degrees, 144 degrees, we may be able to use them for other parts of this. The measure of arc AC is the next one being asked about. From A to C, once again, is a minor arc, given that it's 2 letters, so they are referring to the one that's less than 180 degrees. So minor arc, pardon me for that writing. So we're asking about this one. Now that 43 is going to be helpful. Now that we found it, we can use it for this next part of the answer. So the measure of arc AC, this time I'm going to do a sum of 2 values. Let's just add 67 and 43 and it's taken care of. And that is 110 degrees. Number 12, arc ACD. This time it's not a minor arc, but is it a major arc or is it a semicircle? We're actually going to have to look at the diagram to know for sure. It could be, it looks like it's going to be the semicircle. So this is the one, remember AD was a diameter. So from A to D, like that, will be a semicircle. That's a 180 degree measure. I have nothing to calculate for you here. There, you can, I have things to calculate. I'm not going to calculate anything for you here. Semicircles have a 180 degree angle measure, period. Number 13, arc ACE. Let's go ahead and drag that number over. Let's go ahead and paste that value in. I guess I have to write in those numbers one last time. 43, I believe. 144, I presume. ACE, where's that? So A through C to E. If you recall, oh, actually I have it written. If you recall, we did do the measure of arc AE, and that was the minor arc. ACE is the major arc that hits those 2 endpoints. So this is a major arc. Now, its measure is probably easiest to use by taking 360, the measure of the entire circle, and subtract the 144 that we found for the measure of the minor arc AE. So 360 minus 144 is 216 degrees. Don't forget that degree symbol, by the way, when you're working all these things out. Lastly, number 14, we have arc BEC. BEC is, oh, that's very major. BEC is going to be this B all the way to E or through E into C, like that. Boom, that entire thing, definitely a major arc. BEC, major, major, major arc. And this looks to be the difference between 360 and the 43 degree arc measure that we found. So 360 minus 43, and here we get 200, excuse me, not 200, equals 2, equals 317 degrees. Okay. There are those problems. Let's go to numbers 15 and 16. Tell whether the red arcs are congruent. Explain why or why not. On number 15, what we actually have is basically 2 diameters, 2 lines going through. They do create vertical angles which are congruent, and that would be a good part of what we're referring to because these are central angles. We know they're central angles because they're going through the center, like I said, diameters. Whatever measure of a central angle is the intercepted arc, and I think I navigated through the book a little bit more, and I haven't found this phrase intercepted arc. So intercepted arc means the arc that's captured by your angle here, by the way. So KL, arc KL is the intercepted arc of this angle right there. Anyway, so my point that I was going to make is that a central angle and its intercepted arc have equal measure. And if you have congruent central angles, then you have congruent intercepted arcs. So that's going to be my whole spiel there. Are the arcs congruent? Yes. Arc JM, a minor arc by the way, is congruent to arc KL because vertical central angles are congruent. They're vertical angles, they're central angles, and central angles have, if central angles are congruent, then their arcs are. In number 16, what we have are congruent, not congruent circles. What we have are congruent central angles in 98 and 98. Now, last time I said if central angles are congruent, then their arcs are congruent. That's being in the same circle. That's also true for congruent circles. If these two circles were congruent, meaning the same exact size, then those central angles would mean those arcs at 98 degrees, not just equal measure, but also would be congruent, as in I could place one on the other. But here's the problem. They're not congruent circles. They're not congruent circles. This circle has a radius of 7. This circle has a radius. That's not 15 is not the radius, by the way. It's the diameter. But a radius is half of its diameter. So in number 16, the radius of that circle, that 15 over 2, is 7.5. I don't have, I guess I'll say R equals, but that's in reference to the other, R2, I guess I should say. And R1's radius is 7. Because 7 doesn't equal 7.5, circles aren't congruent. And if they aren't congruent, then it doesn't matter if you have equal central angle measures. Those arcs are not congruent. Arc PQ is not congruent to arc RS because the circles aren't congruent. That's the reason. All right, let's go to number 17. They say find the measure of the red arc in circle Q. Now we have two different drawings. I feel like I want to bring them out over here. This is part of section 10.3 now. I don't know what to do with it yet. I haven't seen these questions before. So this arc EG is, last time we talked about the circles weren't congruent before. These circles are congruent, and that's going to be a helpful thing for us to navigate because whatever's going on over here can help us over here. Congruent circles also have congruent chords. We can feel that with this congruent to that, this congruent to that, and by segment addition postulate bits, the whole chord is congruent to the whole chord here. Congruent chords in either congruent circles or the same circle would have congruent arcs that are captured there. So whatever this arc is over here, this arc is over here, basically. So I need to find the measure of arc BD. Measure of arc BD is 360 minus the sum of these arcs 150 and 110. Let me do this down below. And let me go one step further. I'm gonna talk about the measure of arc EG, the one they're referring to. It's the same as the measure of arc BD because the congruent chords in congruent circles. And so it's going to be, once again, 360 minus this 150 plus 110. So that's 360 minus 260, and that's 100 degrees. That is the measure of the arc in red, measure of arc EG. The 12 wasn't really used other than to indicate the circles were congruent. And those are diameters, by the way. Okay, number 18. 2 questions left. This is going very fast. What? 18 minutes in? Yeah. Let's see. Hopefully I'm not doing proofs. In the diagram, very complex looking diagram, that one that I want to copy over. In the diagram, AC and FD are equal. They both equal 30. Let's see where those are. AC is this guy here. This is 30. It's not degrees or anything. Those are just length units. And FD is 30. So congruent chords, we mentioned something about that before with the arcs, but there's probably more we can say. Those are 30. PG, it's labeled, that's x plus 5. PJ is labeled as 3x minus 1. Find the radius of circle P. You notice that P to B would represent a radius, P to E would represent a radius, but you can also draw your own radius anywhere on here. And I think I really want to somewhere that would make a right triangle, such as this. That could be a radius from P to A. And that would help me with this right triangle here. Now, the way that I'm going to do this is kind of twofold. First things first is these congruent chords. There's a theorem. It goes either way here. When the center, I forget which way they say it. When the center's equidistant from either two chords, basically, yeah, when the center's equidistant from either two chords, then those chords are congruent. But the converse is when two chords are congruent, then the center's equidistant from either of those chords. I forget which way is the original theorem. I apologize on that. But basically, these two chords are congruent. They're both 30, right? They're equal in length. So this is congruent to that, which means I can set x plus 5 equal to 3x minus 1. So stage 1 of this problem to do is solve for x, and you get x equals 3. Now, what does x equals 3 help me do? I can find, say, the length of PG, and I get 3 plus 5, which is 8. And now that I have this length of 8, let me turn x plus 5 into 8. This is one of the sides of this right triangle. Remember this right triangle where they said find the radius? PA is a radius. I can use that one. Radius. Now, 8's one of the legs in the right triangle. Do we know this leg length? We do. Here's another thing that's true. When a diameter, or in this case a radius, is perpendicular to a chord, it also bisects that chord. So these two parts are congruent as well. So I can take that 30 for AG and divide it by 2, and I get 15. So this is 15, this is 8. These are two legs of a right triangle. I want to find that AP radius by using Pythagorean theorem. C squared equals A squared plus B squared. Now, we've done 8, 15, 17. I just gave it away. We've done Pythagorean triples before. This is an 8, 15, 17 Pythagorean triple. So this answer will be 17. Just give me a moment on that. AP squared equals 289, and AP is 17. That is the radius. That is your answer. That is the length. Boom. Okay. We got one more question to go, number 19. It has 3 parts. A circular clock can be divided into 12 congruent sections. True. Find the measure of each arc in this circle. Well, I imagine they're talking about each hour is its own portion of the arc. You know, we have 12, 1, 2, 3, etc. So they're saying find the measure of each of these little parts right here. Boom, 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 boom. Well, there are 12 of them, and the total measure is 360 degrees. So what we'll get to do is take 360 and divide it by 12. And you get 30 degrees each for each section. That's part A. Part B, find the measure of the minor arc formed by the hour and minute hands when the time is 7 o'clock. So the important thing about 7 o'clock, or the top of an hour that we need to know, is the minute hand is on the 12. The minute hand is on the 12, the hour hand's on the 7. Now the 7 would be about right here. The more important part about this is the number of degrees of this minor, well, I guess that's the answer. But the number of hours that go by from 7 to 12, that would be 5-hour difference, right? So 12 minus 7 is 5, and 5 times 30, the number of degrees between each of these guys right here, 9, 10, 11, 12, that's 3 50s. 5 30s. 1, 2, 3, 4, 5. That's 150 degrees. And that is part B. It should be less than 180 as well. Keep that in mind. And the last question of this overall is part C. Find a time at which the hour and minute hands form an arc that's congruent to the arc in part B. Okay, so to get the 150 degrees here, you can reflect this over. We could talk about 5 o'clock. Okay, 5 o'clock could be a valid answer to this thing. Perfect. Because this would also be 150 this way, between 12 and 5. Anything else would be very tricky, even for me to come up with. I mean, I'm sure there's a good math version that I can do, but the problem is, as you course yourself partway through an hour, this fraction starts to move over, right? Between 5 and 6, like, if it hits 5:30, right? If we have 5:30, here's the 5, and here's 30. That's not how this works, though. It doesn't stay on the 5. It goes halfway between 5 and 6. So I'm not going to try and go particular like that. I would just say that 5 o'clock is another time that we can use there. Still 150 degrees for that one. All right, guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching, and that was nice and super quick. How long overall? Yeah, less than 25 minutes. All right, if you have any other questions, please let me know in the comments below. Otherwise, take care. I will see you in the next one.